Welcome back. In this lecture, we are going to be discussing intermolecular forces in molecular substances. In your textbook, it's pages 63 to 70. And by the end of this lecture, you will be able to describe the difference between intramolecular forces and intermolecular forces. You'll be able to explain intermolecular forces in terms of dispersion forces, hydrogen bonding, and dipole-dipole forces. You'll also be able to explain why different compounds have different melting points and boiling points. And you'll be able to compare compounds in terms of their physical properties. So first we'll talk about inter versus intramolecular forces. The bonding forces we've been talking about so far are all intramolecular forces. They're ionic and covalent bonds, the bonds that hold an atom together or hold a molecule together. They're inside a molecule. And so they result from an atom's affinity for valence electrons. So it's all about having stable electron configuration. Now, intermolecular forces are the attractions between molecules, so they're not found in ionic compounds, and they result from molecular polarity. So they happen in compounds that have dipole-dipole forces, or forces where you have polar bonds. And they also result from something called electron dispersion, which is basically the position of electrons. Now, if there weren't any such thing as intermolecular forces, then the only state that would exist on Earth would be gaseous substances. In terms of the molecular compounds, we'd have two choices. Ionic compounds would all be solid, and molecular compounds would all be gases at all temperatures. Now, that's clearly not the case. We have molecular compounds that are solids, liquids, or gases at room temperature, which means there has to be forces, or there has to be something holding molecules together in some compounds, yet not holding them together in other compounds. So, in terms of comparing inter to intra, intermolecular forces are considered weak forces. They're weaker than, these forces are always weaker than ionic bonds and covalent bonds. So those are the strong forces. And intermolecular forces are additive. And what that means is, if a molecule has more than one type of intermolecular force, it means that that molecule has more attractive force to other molecules of its kind. So when we take a look at ionic compounds, in ionic compounds, each ion carries either a positive or a negative charge. This is a static charge, and it's the attraction force between particles. So each positively charged sphere is attracted to each negatively charged sphere, and that's why ionic compounds are always solid at room temperature. Those molecules are so attracted to each other that they stay as close together as possible. For covalent compounds or molecular compounds, each molecule is discrete, with atoms held together by shared electrons, which is what a covalent bond is. Now, as these molecules start to move around, as they move closer to each other, or as they start to move slower, they may or may not be attracted to each other by something called intermolecular forces. And what intermolecular forces are, is they cause two different molecules to become attracted to each other. So, for example, these two molecules might be one part of this molecule might be attracted to one part of this molecule, and a part of this molecule might be attracted to a part of this molecule, and so on. If the attraction is strong enough, the molecules will group together and you'll get something that's a solid. If the forces are too weak, then you'll end up with something that's gaseous, and if the forces are somewhere in between, you'll end up with something in the liquid state. So there's two main types of intermolecular forces, or van der Waals forces. The first one is dipole-dipole forces, and these are caused by polar bonds and polar molecules. So if you have a polar molecule, it means you have a molecule with polar bonds, and hydrogen bonding is a specific type of dipole-dipole force. It's actually the strongest intermolecular force. It's still weaker than a covalent bond, but it's stronger than normal dipole-dipole or everyday dipole-dipole forces, and it's stronger than London dispersion forces. London dispersion forces have to do with electrons, the dispersion of electrons. So we'll start with the dipole-dipole forces. If a molecule in a sample is polar, if the molecules in a sample are polar, then each molecule consists of a slightly positive end and a slightly negative end, or pole. The presence of these positive and negative ends causes molecules to become attracted to one another. The positive side of one molecule will be attracted to the negative side of a neighboring molecule. And we're going to use some examples, or an example to show you what I mean. So here we're going to draw a VSEPR diagram for chloroethane and determine if it's a polar molecule. So first we're going to get our electron count. We have 2 carbons, 5 hydrogens, and a chlorine, which means for our valence electrons we're going to have 4 plus 5 electrons from the hydrogen plus 7 electrons from the chlorine, and that's going to give us 16 valence electrons. Carbon has 4 electrons, or 4 valence electrons. Hydrogens have 1, and chlorines have 7. And so carbon, as usual, is going to be one of our centers because it's the most electron deficient. And I'm going to bind that with another carbon, and now I have 5 hydrogens and a chlorine. Now hydrogen and chlorine are equal in terms of deficiency, so we'll just start putting them on. I'll put a hydrogen here, and a hydrogen here, and a hydrogen here, and a hydrogen here, just to keep it symmetrical. A hydrogen on this molecule, which means our chlorine is going to end up here. And now I'll throw in those bonding electrons. And so the only electrons we're missing are the ones that end up around the chlorine. If we add them up, we'll see that there's 16 there. Our carbons are happy. They both have 8 valence electrons. Chlorine has 8 valence electrons. And hydrogens have 2. So we're pretty happy in terms of our molecule. So now we're going to do our VSEPR diagram. If we take a look, we have a tetrahedral center and a tetrahedral center. They're both AX4 centers. They have no lone pairs and 4 atoms bonded around them. So we're going to have a tetrahedron, and in order just to keep our tetrahedron somewhat simple, I'm going to choose the carbons to be in the same plane, and then so one carbon is going to have hydrogen in the same plane as it. We'll put the 2 carbons in the same plane, and we need one other atom in the same plane. Just for simplicity, I'm going to put the chlorine down here, and then we'll have 1 hydrogen moving away, 1 hydrogen coming towards, a hydrogen moving away, and a hydrogen coming towards. And now, sorry, I gotta draw my hydrogen in here. And now we'll take a look to see if we have any polar bonds. We only have 3 types of bonds. We have a carbon-hydrogen bond. We have a carbon-carbon bond, and we have a carbon-chlorine bond. And so if we take a look at the differences in electronegativity between carbon and hydrogen, the difference in electronegativity is 0.4. Between carbon and carbon, it's 0. And between carbon and chlorine, carbon has an electronegativity of 2.6. Chlorine is 3.2. So we're ending up with a 0.6 difference in electronegativity, and it's pulling towards the chlorine. So the only polar bond would be this one. These bonds are slightly polar. And of course, the carbon-carbon bond is a nonpolar bond. When we draw in our vectors, we see that this polar bond is the only polar bond. And so what this means is right here, we have what's called a dipole-dipole force. The carbon is going to be slightly positive, and the chlorine is going to be slightly negative. If we line it up beside another chloroethane molecule, what we'll see is that these two molecules will have a little bit of attraction for each other. This slightly negative chlorine is going to be attracted to the slightly positive carbon on another chloroethane molecule. And again, this chlorine here is going to be attracted to the carbon of another dichloroethane molecule, and so forth. So what this is your dipole-dipole force. It's the bond or the force between two different molecules. So the force of attraction between two different molecules. A special type of dipole-dipole force is something called hydrogen bonding. The reason it's special is because it's strong. When hydrogen is bonded to an especially electronegative atom such as oxygen, the charge separation starts to approach the charge separation you'd find in an ionic bond. So there's three special forms of hydrogen bonding. They occur when you have a substance that has an OH bond, an FH bond, or an NH bond. So it's called hydrogen bonding because hydrogen is always involved. And then there's three other atoms, and they're very electronegative atoms. Oxygen has an electronegativity of 3.4. Fluorine has an electronegativity of 4.0. And nitrogen has an electronegativity of 3.0. They're also fairly small molecules, which means they're going to be highly attracted to hydrogen's electron. All are highly attracted to hydrogen's one little electron. And the nice thing is, hydrogen only has that one electron. So when you pull that electron away, what you basically have is a proton, or one little particle in the nucleus, a proton, floating around almost by itself. So as soon as you strip that one electron away, you're basically leaving a lone proton all by itself. There's no other electrons around that atom. So the covalent bond keeps that electron to one side of the hydrogen atom, and that hydrogen bond is almost as strong as a covalent bond. Not quite, but almost. And so in diagrams, if there's hydrogen bonding in a substance, the hydrogen bonds are usually shown with a dotted line to indicate that it's weaker than a covalent bond, which is usually a solid line. So hydrogen bonding, for example, a couple of substances. Hydrogen fluoride is the only example of hydrogen bonding that has HF. And so what it would be is a HF molecule. Here's HF, this side slightly negative, this side slightly positive. And it would be attracted to another HF molecule. Again, this side slightly positive, this side slightly negative, and so on. The electrons are all being pulled towards the fluorines, making the hydrogen a positive end, or a positive dipole, and the fluorine a negative dipole. It also occurs in molecules that have OH bonding and molecules that have NH bonds. In terms of, it's especially important in biology. It's responsible for the shape of DNA, and it's also responsible for the shape and function of proteins in our bodies. Here's just an example of what hydrogen bonding would look like. Now, each of these is a water molecule, with the red being oxygens and the blues being hydrogens. And what we have is, here's one water molecule. It has bond dipoles pulling electrons towards the oxygen, because oxygen is much more electronegative than hydrogen, making that end negative. And so what that does is it allows for an attraction between the hydrogen of another water and the oxygen of the water we started with. So each of these three atoms represents a single molecule, and then there's attraction between the molecules. And that's one of the reasons that water, which is really such a small molecule, when you compare it to something like CO2, SO2, NO2, other compounds that only have three atoms are usually gas at STP. Now water isn't. Water is actually a solid at STP. STP, this is 0 degrees Celsius, so water is already a solid, and the reason is because of this hydrogen bonding. As those atoms slow down, or as those molecules slow down, they become attracted to each other and they actually start to stick together. And the reason is hydrogen bonding. These molecules are all gases at SATP because there is no hydrogen bonding in these molecules. An example of hydrogen bonding in DNA. DNA is a two-stranded molecule. It's a macromolecule. It's huge. It's thousands and thousands and actually millions of atoms in size, and it has two strands. One strand would be on this side here. There's one strand of DNA. Here's the other strand of DNA. And they're attracted to each other over and over again by hydrogen bonds. These hydrogens are attracted to this oxygen because they're bonded to a nitrogen. Again, here's a nitrogen. It's being attracted to the hydrogen here because this hydrogen is bonded to a nitrogen. Again, this attraction is happening because one of these hydrogens is bonded to the nitrogen, allowing for large charge separation. So, hydrogen bonding between two different molecules, it happens over and over again in DNA. So we're going to take a look at ethanoic acid and determine if hydrogen bonding is present in ethanoic acid. So we're going to get, now this is a bigger molecule, but if we take a look, we can kind of see that carbon's in here twice. So we know that carbon, here we know that there's at least one center here, and we're going to make a new center here because they've separated the carbons. If the carbons weren't centers, they wouldn't be separating them from each other. So we'll start with getting our electron total. We have 3 carbons plus 6 hydrogens, and again, because in the formula the hydrogens were separated, we're going to assume that there's at least some separation between the hydrogens, and 2 oxygens, leaving us with 4 electrons times 3 plus 6 electrons plus 2 times 6 electrons, and that's going to be 12, 24, 30 valence electrons. And again, if we take a look at our atoms, carbon is going to be our center because it's the most electron deficient. And so what I'm going to do is, when you have carbon atoms in a molecule, chances are they're all connected to each other in a chain. So I'm going to do it. There's my 3 carbons. On one end, I'm going to put my hydrogens. I can get 5 of them around here. That leaves me with an oxygen, and then an oxygen, and I'm going to bind the hydrogen to it. And now we'll put in our electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I need 10 more electrons. The only places they can go, this carbon has 1 more. We'll go, so this carbon has 1 orbital there, so there's 1, 2, 3, 4, 5, 6. We can only add 4 more, so I'm going to add them to oxygen, and I'm going to add 2 to each. And we can see that this oxygen here is missing an electron, this carbon here is missing an electron, so we can form a double bond in our compound. And so if we take a look at our centers, we actually have 4 centers. We have 3 carbon centers and an oxygen center here. And our centers are AX4, AX4, AX3, and this oxygen center, it'd be an AX2. Sorry, wrong. Yeah, this is the wrong center. Sorry, down here. This is a center because it has more than one atom bonded to it. It's an AX2. It also has 2 lone pairs. So in terms of shape, we got a tetrahedron, a trigonal planar, and a bent based on a tetrahedron. And so now we can draw, and what I'm going to do is we're going to keep as many things as we can in the same plane. So we're going to keep our carbons in the same plane, because each of these carbons, well, the first 2 carbons have 2 atoms each that are going to be off the plane. The trigonal planar atom has 3 atoms in the same plane, so we'll do that. And oxygen, this oxygen here has a bent shape, so we'll finish the oxygen. And so again, that hydrogen's in the same plane, so we'll keep it in the same plane. And that last oxygen, we're going to draw the double bond in, even though this is a structural diagram. So there's our triangle around that carbon. And now our other carbon, I'm just going to erase those lines. I just wanted to show you the trigonal planar shape. Okay, so now we have our shape, and now we're going to check for bond polarities. Oh, sorry, I forgot about our hydrogens here. So let's get our other 5 hydrogens on our molecule. So these 2 hydrogens we'll put in the plane. Actually, this hydrogen we can't put in the plane, so we'll make this one come out. This one will go away. This one will come out. And this one will go away. And now we'll take a look. We know that, we'll see what types of bonds we have. We have a carbon-hydrogen bond, carbon-oxygen bond, and a oxygen-hydrogen bond. Those are the 3 types of bonds that we're going to be looking at the electronegativity of. And we know that this one is slightly polar. Carbon-oxygen is polar, and oxygen-hydrogen is very polar. This is actually this causes hydrogen bonding. And so if we draw these dipoles on, what we'll see is this hydrogen on the end here is positive, this oxygen is negative, this oxygen is negative, and this carbon is slightly positive. So what we see is electrons are being pulled to our oxygens, and they're being pulled away from carbons and hydrogens. What this means is if we line it up beside another molecule that has hydrogen bonding, and we'll just draw the end of one of these molecules here. So here's part of another ethanoic acid. What we have is an attraction between the hydrogen of one molecule and the oxygen of another. So this here would be the hydrogen bond. So it's the attraction between 2 molecules. So it turns out that those are the attractive forces in polar molecules. There also has to be some kind of attractive force in non-molar molecules as well. Otherwise, all non-polar molecules would be gases, and they'd all have the same melting points and boiling points. So if we consider some examples, each of the examples listed here, carbon dioxide, hydrogen gas, fluorine gas, chlorine gas, iodine, and iodine's not even a gas, it's actually a solid. So we can see that the attractive forces inside iodine are stronger than the attractive forces of the other molecules listed, because it actually holds those molecules together into a solid. So each one has to have differences in intermolecular forces. There has to be something holding those molecules together in some of those substances. So it's a force on which polarity doesn't apply, and it's called London dispersion force. So if we take a sample of chlorine gas, what chlorine gas is it consists of two chlorine, each molecule is two chlorine atoms sharing two electrons. So they're sharing these electrons in their valence energy level, but at the same time, the electrons are being simultaneously attracted strongly by both of the nuclei of both of the atoms. So, yet these atoms show a strong tendency to stay together, and they're held together by a covalent bond, so that covalent bond has to be strong, because if it wasn't, the molecule would be torn apart. And so what happens is electrons are always moving rapidly, and they're in constant motion, and occasionally they can become unevenly distributed around a nucleus. So instead of them all being nicely spread out around the nucleus of an atom, they get dispersed unevenly, and what this does is it creates a temporary dipole. If you imagine two chlorine atoms, and they're sharing electrons, and then they have their valence shells. But you have to remember, chlorine has more than just its valence shell. It also has those inner shells. It actually has three energy levels. So there's lots of electrons around one chlorine and lots of electrons around another. Now, occasionally what will happen is all the electrons on one chlorine will gather to one side of the molecule. And what that does is it creates a slightly negative part to the molecule and a slightly positive part to the molecule, only for a split second. But what that does is it creates a temporary dipole in a neighboring molecule. So because this one has a temporary dipole for a second, neighboring chlorines are going to end up having temporary dipoles as well. All the electrons in this molecule will start shifting to this side, creating a slightly negative part to the molecule. As that happens, this side becomes slightly positive. And then you have another very quick, very temporary dipole. And so even though they're quick and temporary, you have to remember that even a small sample of molecules is going to have trillions and trillions of atoms. So in a sample of trillions of atoms, there might be a million temporary dipoles existing at one time. And so they add up. In molecules where you can get lots of dipoles, you end up with lots of London dispersion, and it's a force that's going to keep those molecules close together as they create temporary dipoles throughout the entire substance. So the strength of the London dispersion force, or these temporary dipoles, depends on a couple of things. The first thing it depends on is the number of electrons in the molecule. If you have a lot of electrons, it's easier or more likely that they'll become unevenly distributed over time, even for a second. The other thing that affects London dispersion, and it's a little less measurable in terms of being able to tell the difference, but the shape of the molecule also affects its London dispersion force. If the molecule is long and drawn out, then it's easy to disperse electrons unevenly because you have this long chain, and as soon as you start to, so if you have a lot of atoms in a chain, as soon as you get a few electrons over to one side, it's easy to get more being pulled along the way, and you end up with positive and negative ends to the molecule. If you have and because of this, they approach each other and they're in the solid and liquid state. So linear molecules have stronger London dispersion than spherical molecules. In a sphere, the electrons are less likely to be able to make it around the atom, or around the molecule. Sorry, a little bit of a brain blank there for a second. So, intermolecular forces in molecules. All molecular compounds have London dispersion forces because they all have electrons. So all molecules have London dispersion. Only polar molecules will have dipole-dipole forces. So when you have dipole-dipole forces, if you see a molecule with dipole-dipole forces, chances are it's a stronger force than just London dispersion, and so that's going to affect which molecule will have a lower melting point or boiling point. And intermolecular forces are additive. Dipole-dipole forces, if NH, or FH bonds exist, then it's going to be hydrogen bonding, which is just a form of dipole-dipole bonding. And intermolecular forces are additive, so molecules that have all three forces are going to have very strong intermolecular forces, which means molecules of that substance will be strongly attracted to each other. So, for the next lecture, we will be explaining why different substances melt and boil at different temperatures using the concept of intermolecular forces. So, we're going to explain why something like carbon dioxide is a gas, but water is a liquid at room temperature, even though, if you look at their size, they're both about the same size. They both have 3 atoms. They both have similar molecular masses. So we'll be looking at why one's a gas at room temperature that has very little intermolecular force, and why the other, water, is a liquid at room temperature, which means it has fairly strong intermolecular forces.